Welcome to the Problems Channel Season 3, Episode 30, the episode which I titled A Loxodrome, a deduction of an equation, because in this episode we will do precisely that. We will show a way to deduce an equation of a Loxodrome. But before we deep dive into the underlying physics and mathematics of the matter, as a traditional and friendly reminder, if you're joining our channel mid-season, especially after Season 1 and Season 2, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material presented on this channel is for you to go to the home page of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety and follow all the instructions that were given that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on this channel that is of interest to you and use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current supporters and the current subscribers of our channel. In the physics problem S3P7, we're asked to deduce an equation of the trajectory of a point that moves over the surface over a rigid sphere in such a way that that trajectory forms one and the same constant known and given ahead of time angle beta with each and every meridian of that sphere. Not just one meridian, not two, not three meridians, but all meridians on that sphere. In other words, doesn't really matter which meridian of that sphere the point intersects, the angle at which it does so must be the angle beta. The point intersects, for example, this meridian at the angle beta, this meridian at the angle beta, this meridian at one and the same angle beta, and so on, everywhere. And meridians are the lines that run in this drawing over here, roughly, let's say, north to south or south to north. So this is a meridian, this is a meridian, this is a meridian, and this is a meridian. And we're asked to deduce that equation in the so-called Earth fixed or Earth-centered coordinate system. And as a friendly reminder, in such a coordinate system, we have how many real numbers that define the position of the point on that sphere completely. We have two such numbers, and that means that in some sense the sphere is not a three-dimensional actually, but a two-dimensional object as far as we're concerned, because two real numbers lock in the position of a point on the sphere of one and the same fixed radius completely. And these two numbers are the longitude, or a longitudinal angle, lambda, and the latitude, or the latitudinal angle, usually defined or portrayed with the Greek letter phi. This segment in which we describe how an Earth-centered, Earth-fixed coordinate system that you can see on the right side of your screen is constructed is optional. If you feel at home with such a coordinate system, then you can safely move on to the next segment and skip this one, unless of course you want to try to solve a nice little puzzle that I will discuss with respect to the Earth-centered, Earth-fixed coordinate system at the end of this segment. I have anchored it with its own time point, so it will be very easy for you to find in the timeline of this episode. As such, an Earth-centered and Earth-fixed coordinate system can be put together or constructed as follows, under assumption, of course, that we model Earth with a sphere, and a sphere is just one of several possible models of Earth. So let us say we're given a sphere with a known location of its center. Such a sphere at random, which means at any point on that sphere whatsoever, we pick a point and we name it either N for North Pole or S for South Pole. It doesn't really matter which name you decide to bestow on such a randomly picked point. For demonstration purposes and for definitiveness, we will pick this point over here, let's say, and we will name that point N for North Pole. Now that we have two distinct points, the point N and the point O, two such distinct points define a unique straight line in the ambient 3 space with the usual embedding of the sphere into the 3 space, and that unique straight line will intersect our sphere at two distinct points that will be diametrically opposite of each other. And the first such point will be N, this is by design, and the second such point will be the point S. We will name it S for South Pole. Let's say this point is located right here. We will name it S. And in the spherical geometry, these points are called the antipodal points, and then evidently the line segment. And S will be a diameter of a sphere, which is another way of saying that the points N, O, and S are collinear. Now recall that in the plane we have such an object called the perpendicular bisector of a given line segment. This is a straight line shown over here. It runs perpendicular to such a line segment and it cuts it in half. The 3-space analog of a perpendicular bisector in the plane will be the perpendicular bisector plane, not a line, but a plane. And with respect to the points N, S, and O, such a bisecting perpendicular plane will be unique. It will be perpendicular to the north to south diameter of that sphere. It will cut it in half, and every point of such plane will be equidistant from these two antipodal points, the point N and the point S. And such a bisecting plane, let us pretend that this piece of office paper is an incredible simulation of a plane. When that plane bisects the line segment in a perpendicular fashion, the intersection of that plane with the parent sphere will produce an object known as a great circle, and that great circle will be called the equator of the sphere, and the plane that perpendicularly bisects the diameter ns of the parent sphere will be called the equatorial plane. Now the equator divides our sphere into two logical halves, the northern hemisphere and the southern hemisphere. And once we concentrate on the diameter ns of our sphere, we observe that there exist uncountably infinitely many planes that contain the line segment ns, and that are perpendicular to the equator, or that are perpendicular to our equatorial plane. And the reason there are uncountably infinitely many such planes, because for each number taken from the subset of real numbers 0 to pi, there corresponds a plane. For example, we can pick one plane to be the reference plane, and with respect to that reference plane, we rotate all the other planes by the angular amounts taken from this subset of real numbers. We rotate these planes around the diameter ns, and every time such a plane intersects the given sphere, then another great circle results. That great circle, however, will pass exactly through the antipodal points, N the North Pole and S the South Pole. Each such plane will generate the corresponding great circle that passes through these two antipodal points, And each such great circle is partitioned by these 2 points, antipodal points, into 2 logical halves, and each such half is called the meridian. And this is actually what you see on the right hand side in blue over here, partially 1/2 of one meridian. That means that, for example, if we portray one such meridian, then such a meridian will be designated over here. Let's write it down over here. Will be a meridian. And then remember that each meridian, let's say, originates at the North Pole and terminates at the South Pole of the sphere, or conversely originates at the South Pole and terminates at the North Pole. But all the corresponding great circles thus constructed that pass through the North Pole and the South Pole precisely intersect at these 2 antipodal points, and we now understand that there will be uncountably infinitely many such great circles and uncountably infinitely many meridians. So theoretically, from a purely mathematical standpoint, there will be uncountably infinitely many such meridians, but that may not be the case in practice. And now that we understand how meridians come into existence, one such meridian picked arbitrarily can be called the reference meridian. So with that reference meridian, we will measure the angular displacement of any point that is located on our sphere in two directions, the westerly direction and the easterly direction. In other words, the plane that generates this meridian, or that great circle, partitions our sphere in yet 2 other logical halves, the western hemisphere and the eastern hemisphere. Compare it to the 2 hemispheres into which the equator partitions, or the equatorial plane partitions the sphere, the northern hemisphere and the southern hemisphere. And if we designate this reference meridian, or associate this reference meridian with the 0 angular displacement, then this is precisely how the longitude, lambda, comes into existence. Because, for example, let's say we measure this angle right here as lambda. This will be called the longitude, and we can see that, let me erase this, the longitudes can be measured again from a purely mathematical perspective. That doesn't mean that this is how done in practice, but we're concerned with purely mathematical setup. So purely mathematical, the longitude can be measured with positive real numbers, with negative real numbers, and again we choose in one direction that is positive, so this will be the numbers from 0 to pi, and this will be numbers from the negative numbers will run from 0 to negative pi. Lastly, there exists yet another set of uncountably infinitely many planes, each of which is distinct from our favorite equatorial plane, but which is parallel to it and intersects the north to south and S diameter of that sphere. The result of the intersection of such a plane with the parent sphere will be a circle that has a strictly smaller radius than the radius of the equator and a strictly shorter or smaller length of its circumference. And these circles will get smaller and smaller in their radius until they converge into the North Pole if we step from the equator in the northbound direction, and they will get smaller and smaller and smaller, and they will eventually converge into a point that is the South Pole if we move in the southbound direction. So let me, for example, depict one of such circles in the northern hemisphere and in the southern hemisphere. There we go. Let's pretend that this is one such circle and then the other such circle. Now these circles are called parallel. So one circle will be a parallel, and that is how another coordinate in the Earth-fixed, Earth-centered coordinate system is introduced because any point on the sphere will have a certain angular displacement with respect to the equatorial plane or with respect to the equator, and this angular measurement constructed as follows. We take the center of the sphere to be the center of the corresponding angle, and let's say here we have our point located over here. Then we connect this point with the center of the sphere this way, and then we measure the angle from the equatorial plane in the corresponding direction. So here we will measure this angle this way. This angle is called a latitude. So let's say this will be a longitude is lambda. This is the longitude, and this will be the latitude. So theta will be the latitude, and you of course understand that by now that the latitude can be measured also with positive real numbers and with negative real numbers. In the first case, we will measure them by real numbers that range from 0 to positive pi over 2, and in the negative case, they will run from 0 to negative pi over 2. Again, which one we pick to associate with which, it doesn't really matter, but purely mathematically, let's say the numbers that reflect the position of the point in the northern hemisphere will be measured from 0 to positive pi over 2, and in the southern hemisphere from 0 to negative pi over 2, and that is how these numbers come into play. So now a short quiz for you to see if you understand how the Earth-centered, Earth-fixed coordinate system is constructed. Remember that the center of the sphere, in this case O, the point O, is the origin of this coordinate system. One more time in the lightning round, we pick any one meridian at random arbitrarily to be the reference meridian, and we will measure all the positions of the points on the sphere with respect to this meridian in the westerly and easterly direction, with two sets of positive numbers from 0 to pi or from 0 to negative pi. And then we pick, again, constructed in such a way that O is the vertex of the corresponding angle, the angular displacement of a point on the surface of the sphere with respect to the equatorial plane or with the equator will be the latitude, longitude, latitude. This is exactly what you see on the right hand side of your screen: longitude, latitude, and our point P. So we'll jump to it in a second. But here is the question: what is the set of points on the sphere, each of which has one and the same or fixed longitude? And the answer to this question is a given meridian. You see, if a point traverses the surface of a rigid sphere in such a way that its longitude remains one and the same at all times, then such a point, for example, can originate its motion from the South Pole and move along the meridian to the North Pole, and conversely, such a point can originate its motion from the North Pole and move along the corresponding meridian all the way to the South Pole, and at all these times the longitude of that point will be one and the same. So this is the set of points that have one and the same, the set of points on the surface of a rigid sphere that have one and the same longitude. And likewise, what is the set of points on the surface of a rigid sphere for which a point that executes the motion over that surface has one and the same latitude, fixed latitude, phi? Well, if it has the fixed latitude phi, let's write it this way, phi, then it should be evident by now that such set of points will be exactly a parallel. So if a point runs along a parallel, like so, executes the motion like so, then its latitude will remain one and the same. And again, for those of you who can think spatially or like to think spatially. So the question is this: if a point traverses a set of points on the surface of the rigid sphere with the same longitude, or runs along one and the same fixed meridian, then let's say we have a radius vector that originates at the center of the sphere or at the origins of this coordinate system, Earth fixed, Earth centered, and terminates at that moving point. And if such a point runs through one entire, let's say, one entire meridian, what type of geometric shape this radius vector will sweep? And the answer is, of course, is that it will sweep exactly half a circle like this. This is called a lamina, 1/2 of a circle. Likewise, if a point executes a motion, one complete revolution over the same one and the same parallel, or having the latitude one and the same, phi, then what type of a geometric shape will its radius vector sweep? Well, the answer here is that in this case, the radius vector will sweep the right circular cone, and the vertex of that cone will be the origin of our coordinate system. All the generatrices will be the particular instances of the radius vector, and its base will be exactly the plane which generated this particular parallel, the plane that was intersected with the plane perpendicular to the diameter NS. So now you should be more comfortable with understanding how the Earth-bound, Earth-centered, Earth-fixed coordinate system is constructed. And as the last bit of interesting information, with this particular situation, with this particular coordinate system, there exists a nice little classical by now puzzle. The way it goes like this: we stand somewhere on the surface of a rigid sphere, we walk 1 mile south, 1 mile west, 1 mile north, and wind up at the same spot. Where on the surface of that rigid sphere can we be standing so that this constraint is honored? Well, one answer that most people get, of course, right away is the North Pole, because any direction we go from the North Pole will be the southbound direction. So we go south 1 mile, then we go west 1 mile, and then we go back 1 mile up north, which traverse the so-called equilateral spherical triangle, and then we wind up at the same spot that we started from. So our initial walk will be along what? Along a certain meridian. Then we will walk westward along what? Along a certain parallel, and then we'll climb back along another meridian. So this shape will be an equilateral spherical triangle, and that is one solution. Many people get that, but just likewise, many people miss uncountably, infinitely many other solutions on the surface of a sphere that satisfy the same constraint. And all these solutions dwell on the other side, around the antipodal point at the south pole of the planet. And the way it works is like this. Over here, look at this, right around the south pole of the sphere, there exists a parallel, which is basically a circle that is formed by intersection of the sphere and a plane that runs perpendicular to the diameter of that sphere, NS, and has, let's say we'll designate it as C1. The circumference of that parallel, the circumference of that circle, is 1 mile. That means if we start somewhere 1 mile north of that 1 mile long parallel, then we walk 1 mile south, we traverse one circle, we clock in 1 mile in the westbound direction, and then we walk back up northbound for 1 mile, and we wind up exactly where we started from. The trick is, however, is that the starting point for our southwest north journey can be located anywhere on yet another parallel that is located 1 mile above our 1 mile long parallel. And there will be uncountably, infinitely many starting points on the surface of a rigid sphere that satisfy this constraint. And now if you understood this maneuver, then there will be another, still closer to the South Pole, there will be another parallel over here, the smaller one, the length of whose circumference will be 1/2. You see, we'll designate it C 1/2 of a mile. Again, starting 1 mile north of that 1/2 mile long parallel, we satisfy the constraints of the problem. We walk 1 mile south, then we make 2 circles. By making 2 circles, we still clock 1 mile in the westbound direction, and then we climb back up north and come back to the point that we started from. Also, uncountably, infinitely many such starting points that lead to the parallel that has the length of its circumference 1/2 mile. Then just like that, there is another parallel whose length is 1/3 of a mile, so we make 3 circles. There is another parallel that's 1/4 of a mile, 4 circles, 1 mile, but if we walk westward, we still clock in the same mile, and so on. So basically, there exists this time, there will be countably infinitely many for each n over here, parallels such that if we make n circles around it, we will clock in 1 mile and the whole thing will work. And now that we understand how the Earth-centered, Earth-fixed coordinate system is put together, we can move on and solve the problem at hand. As such, let a point P execute the motion over the surface of a rigid sphere in such a way that its trajectory forms one and the same constant angle with all the meridians of that sphere. Not just 1 or 2 meridians, but all the meridians. No matter which meridian the trajectory of the sample point P intersects, it does so under one and the same, let's say given ahead of time, angle, which we designated with the lowercase beta shown in yellow on the right side of your screen. And under these conditions, we seek to construct a certain functional dependency or a functional relationship that ties together the two coordinates or that reflect the 2 degrees of freedom of our point, the longitude lambda and the latitude phi. That can be done in a number of different ways. For example, one way in which we can deduce such a relationship is by using the so-called quadratic forms from differential geometry, but it takes a while before students get proficient with manipulating such quadratic forms, and in order to make this deduction accessible to the widest audience possible, we will deduce that relationship using the notions from physics, or in some sense one notion from physics, the velocity, the notion of velocity, plus we qualify this problem as a problem in physics. And back in my time, like I said before, this could be a very nice, a traditional conversation starter for a verbal face-to-face real-time interrogation theoretical physics exam, where you're expected to solve this problem inside of, let's say, 5 or 10 minutes. This is just a warm-up for the upcoming conversation. And one way we will do it, in perhaps this keeping it as simple as possible but not simpler way, is by using or making the following 2 key observations. The first observation, which we can mathematize, if you will, is the following. Remember that our point P remains on the surface of the rigid sphere at all times. That point does not separate from the surface of the sphere going outward or going inward. It always stays on the surface of the sphere. And what does that mean? That means that the radial velocity, which I will designate with the VR, remains constant, and it remains 0 at all times. In other words, if we say that t r over dt by its length is 0, that means that this distance from the origin of our coordinate system to the point P does not change, and it remains one and the same, designated with the uppercase R at all times. That means that, again, the radial velocity of the point is 0, and does not change. That is the observation number one. Observation number two comes down to the mechanics of how we measure the angles between two curves. Evidently, we think that the shape of the trajectory of the point P will be some spatial curve, and we already know what a meridian is. A meridian is 1/2 of a great circle that originates at one pole of the sphere and terminates at the other pole. It's the antipodal point. And how do we measure the angle between such two curves? Well, by definition, the angle between two curves is the smallest angle between the corresponding tangents. And what are the things that come to mind when we speak of tangents to curves? Well, if one curve is a trajectory, then we know that the vector of velocity of a moving point is what? Is tangential to the trajectory at that point. And here is the key observation. The total velocity of our point P should be decomposed into a vector sum of two components. The latitudinal velocity v phi shown over here, pointing this way, and longitudinal velocity v lambda that points this way, also shown in red as a vector over here. And in sum, the longitudinal velocity v lambda and the latitudinal velocity v phi sum to the total vector shown in blue. The vector v points this way as a sum of these two component vectors. And how are these vectors positioned in space? Well, look at this. We have our meridian. And again, remember that practically that may be not so, but purely theoretically, no matter which point on the sphere our traveling point P occupies, there is always a meridian passing through it. So we have, in some sense, semicircle, or in general, we have a circle at that point. Our sphere, which is a quite nice surface in the old days, these days it's a manifold. It possesses a tangential plane at every such point. At the point P, our sphere possesses the tangential plane, and in that plane there will lie a straight line that is tangent to our meridian at the point P. Let's say it will run like so. This is our tangent to the meridian, which is basically a great circle that passes through two antipodal points, which we refer as the North Pole and the South Pole of the sphere. And in the direction, in the same tangential plane, in the direction perpendicular to that tangent, like so, there will lie the longitudinal velocity, v lambda. And along the tangent to the meridian at the point P, there will point the component which is the latitudinal velocity v phi. And again, the vector sum of these two vectors will form the complete vector. And this is how we measure the angle between the trajectory, the mysterious, not known to us yet curve, and the meridian. This is the angle between the complete or the total vector v and the latitudinal velocity v phi shown in red over here. This is the angle beta. This is the angle that must be constant. So this is the key observation. So once we have that, and this is our rectangle here, or a right triangle here, then we take the magnitudes, not the vectors, but the magnitudes of our velocities, and then we write pretty much the middle school definition of this angle for the cotangent of the angle beta. That is the constant angle between our trajectory and every meridian is equal to what? It is equal to the adjacent side divided by the opposite side. So it will be the latitudinal velocity v phi divided by the longitudinal velocity vl. So now the question is what these velocities are, but this is more than straightforward. Look at this. The latitudinal velocity v phi keeps track of the angular displacement of a point with respect to the equatorial plane, this angle phi over here. And that means that at any instance, that point belongs to a circle of radius r, And then what is the, if you remember this from, let's say, your high school days, the length, the arc length of the circle will be the radius of the circle times the small increment in this angle. It will be d phi. If we divide this by dt, then we will have exactly our latitudinal velocity. In other words, we will say that the latitudinal velocity v phi will be one and the same radius of the sphere times d phi over dt. That much should be understood. This is nothing in some sense more than the angular velocity of a point as if it were moving just over the corresponding great circle of radius r, or this part of that circle to which we refer as the meridian. Now we move on to the longitudinal velocity v lambda. This is also not very complicated, because if we for a moment cancel the latitudinal motion and only consider the motion in this direction, which tracks what? The longitudinal velocity keeps track of the rate of change of the angular displacement of our point with respect to the reference meridian, which I did not show to avoid the clutter, but let's say this is our reference meridian. This is 0 for the longitude, the initial point. And what does that mean? Well, that means that, again, if we abstract ourselves from the latitudinal motion and only consider the change in the longitude of a point, then what kind of motion the point P executes? Well, it will execute the motion over, remember, a parallel. And what is the radius? Well, this will be the radius of this parallel, so it will run like this. See, somehow like this. And the point P will be projected orthogonally on our favorite NS somewhere here diameter of our sphere. We'll obtain the point Q. So this will be the radius of the circle that is traversed by the point P, again in the absence and under the obstruction away from the longitudinal velocity. Just one motion over the circle of radius r, or the distance pq. So there you go. The longitudinal velocity of our point will be the distance pq. This distance evidently will change times d lambda dt. Again, this is nothing too complicated. This, in some sense, this is the good old middle school motion over circle of a given radius r, p, the distance pq. Then this is the angular velocity, the angle over dt, the angle we call longitude, lambda. So there you go. And how do we express the distance between the points P and Q in terms of the given material? Well, remember, by the age of 23, Isaac Newton knew the so-called Euclid's elements back and forth like the back of his hand. So this is the theorem from the Euclid's elements, book 1. We have, look at this, two straight lines, this straight line and this straight line. This angle is right, are what? Are parallel, and this line falls on two parallel straight lines. It means that this angle, to which we refer as the latitude phi, must be equal to this angle by magnitude. So what is the distance pq? Well, it will be the radius of our rigid sphere r times what? Cosine of theta. So here we go. This is r times cosine of latitude times d lambda dt. And this is it. Game over. It's actually not that difficult. That's why you're expected to solve this problem in a space of 5 to 10 minutes in the verbal examination, the verbal theoretical physics examination format. Let's put this results back into our original formula. So for the latitudinal velocity, we have r times d phi over dt times what? The reciprocal of this material over here. So we'll have dt will go into the numerator here. We will have r times cosine of phi times d lambda. You see, the radius and the radius cancel out, the first differential of time cancel out, and let's write it over here. The cotangent of beta is equal to d phi over cosine of phi times d lambda, and this is perhaps one of the more pleasant differential equations that you can wish for. We can separate the variables. We can move d lambda from the denominator of the right hand side into the numerator of the left hand side, and what will we have? We will have a constant real number, cotangent of beta, times d lambda is equal to d phi over cosine of phi. And now, what is the next maneuver if you were solving this problem on your own? Exactly. We will integrate both sides of this relation. At this point in your mathematical career, you should be able to handle these integrals on your own, but just in case, in order to make sure that everyone is on the same page, I will show you a way how this integral can be evaluated, because we're dealing with trigonometric functions, and the possibilities to express one and the same material with trigonometric functions blossom. There are many different ways. Here is just one way. We start from a phi. Remember that the trigonometric function of sine can be expressed which way? This is the journey begins. This is just one way, for example. It can be by the double angle identity. It can be expressed as follows: sine of x over 2 times the cosine of x over 2. You see, well, in some sense, we can also do the same thing for sine of x over 2, and like a splitting amoeba or like a splitting cell, we can keep growing this half and half and half and so on. But this is enough. Why? Because when we integrate this guy over here, dx over sine of x, which way we can do it? Well, we can use precisely this representation. Look at this. Dx over 2 times sine of x over 2 times the cosine of x over 2. 2 can be safely moved under the differential with no ill effect. So in some sense, we can say dt sine of t times the cosine of t, but let's keep it this way. So what do we do now? Well, what we do now is the following maneuver: d of x over 2. And then look at this. We'll loiter over the denominator of this integrand. We multiply it by the cosine of x over 2, raising this cosine to the second power. And we divide by the same cosine of x over 2. Once we divide by the cosine of x over 2, and here we multiply, what do we obtain in the denominator? Well, this will be the tangent as a trigonometric function of x over 2 times the cosine square of x over 2. And this is, again, goes to the origin of very simple differential equations. What is this? What is this guy right here? Well, this is the first differential of the trigonometric function of tangent of the same argument. So in some sense, we can write it like this. It's integral d what is this? The integral of d f of x and then f of x. And what is this? It will be the natural logarithm of f of x plus a constant, with the understanding that f of x is tangent of half argument. So log absolute value of tan of x over 2 plus a constant. And then from your real analysis, mathematical analysis, or whatever other course, you know that for all x real, what do we have? That sine of x plus pi over 2, let's say theta, will be the cosine of theta. So for all theta real, sine of theta plus pi over 2 is cosine of theta. So the question is, how do we manufacture the cosine in the denominator over here when we know how to compute the integral of reciprocal sine, knowing this here identity? Well, we simply replace x with x plus pi over 2 dx plus pi over 2. This whole thing becomes this integral right here, and now we replace our x for the integral over here, for the result over here, with what? We replace this with x plus pi over 2, and then from here it follows what? The integral of d, well, in our case it will be phi over cosine of phi. We simply look at this guy, look at this relation, and write down the result. The natural logarithm of absolute value of tangent of x over 2 plus pi over 4 absolute value plus a constant. Again, make sure that you understand how these things came about. This is phi. How these things came about: we manufactured the cosine out of the sine by replacing uniformly all the material in this integral with x plus pi over 2. But in the original integral we had what material? Just x over 2. So when x becomes x over 2 plus pi over 2, x over 2 plus pi over 4, and that is the result. And now that we understand how the integration of this very, very straightforward differential equation unfolds, this is a baby differential equation, or as a happy differential of an equation that you can get, equation with separable variables, we obtain the following. The trigonometric function of cotangent of beta, the angle in question between the trajectory and every meridian on our sphere, times lambda plus certain constant, which we can write which way? Natural logarithm of e raised to the power of c, the constant, is equal to the natural logarithm of an absolute value of tangent of latitude half plus pi over 4. We absorb this constant into this constant, we raise it into the power, use it as a power for e, take the log, and when we potentialize this relation over here or use each side as the power of the base of the natural logarithm e, we will have essentially the following result. We will have the trigonometric function of tangent of latitude half plus pi over 4 equal to some constant, doesn't really matter, at some point c, times e raised to the power longitude, lambda, longitude, times the trigonometric function of cotangent of beta. In some sense, this is the equation that you were expected to generate on your own. A functional dependency, or a functional relation that ties together the longitude and the latitude of the point. And in some sense, you can solve this equation also for lambda, leave it with the certain constant, and write it as an expression of lambda equals. This is already trivial business. The other slightly different way to look at it, because now we have actually a nice, delicious, or wonderful pool of very sensitive functions with interesting properties. We have the logarithm, we have the tangent, we have the cotangent. Wonderful stuff. What we can do is we can integrate this equation over here as follows. For example, we can write down the following: cotangent of beta, and here we integrate d lambda, the position of the point on the sphere as far as its longitude is concerned, from the longitude of origin to the longitude of destination point. Let's say we have 2 points on the sphere, from A to B, for airplane to fly, or for a boat to sail over the ocean. And then here we will integrate the right hand side from the latitude of origin to the latitude of destination, d phi over cosine of phi. That maneuver is understood. Longitude of origin, longitude of destination point, latitude of origin, latitude of destination. We know this integral, so what will we have over here? Well, we will say that the cotangent of beta in this case will be what? It will be 1 divided by lambda destination minus lambda of origin times the natural logarithm of this is going to be quite monstrous expression. What will it be over here? We'll have the latitude of destination, so trigonometric function of tangent, latitude of destination over 2 plus pi over 4 divided by trigonometric function of tangent, latitude of origin divided by 2 plus pi over 4. And the reason for different forms over here is that when you'll be doing research and developing your better understanding of how this shape, how this particular curve, which is actually called a Loxodrome or the rhumb line, how it behaves. For example, one way to look at it is to ask ourselves, okay, we derived a certain, what we call an equation of Loxodrome, of the point that moves over the rigid, over the surface of a rigid sphere. It has these properties, but will it submit or will it work with the common sense? Let's say our point runs over, as we mentioned before at the opening segment, that the set of points on the sphere in the chosen Earth-centric, Earth-fixed coordinate system, they have one and the same longitude, lambda. It will be what? Well, it's going to be corresponding meridian. So if our point executes the motion over the surface of a rigid sphere along one and the same meridian, the angle beta will be what? The angle beta will be 0. So when the angle beta is 0, the sine at 0 is what? It will be 0. When we divide by 0, bad things happen. So what do we need to write? We need to write the limit. We need to be careful, and we write to when b tends to 0, and then again we need to be careful because different branches of the trigonometric function of cotangent, they behave differently at one and the same point, where the cotangent tends to positive infinity depending on the side. It could be positive infinity, it could be negative infinity. It's discontinuity of the second kind between different branches. But when beta tends to 0, let's say from the positive side, we have cotangent of beta will be tending to positive infinity, and when we have it to when the cotangent of beta is positive infinity, then correspondingly what will happen over here? Here, this power will be e raised to the power that tends to positive infinity. Again, in the limit, we will have positive infinity, and in the limit, what will happen to the angle var phi over here? Well, you will have to see what's happening. The angle apparently will tend to what? To pi over 2, if I'm not mistaken, but you get the point. You should be able to see that, yes, indeed, our point will traverse the meridian. Likewise, when the angle beta, let's say beta, tends to pi over 2, positive pi over 2, so our point always runs perpendicular to each and every meridian. In this case, the sine of pi over 2 is 1, the cosine is 0, e raised to the power of 0 is 1, so this is a constant, this is a constant, so this must be a constant over here. So that makes sense, because then in this case we see that the latitude of a point that travels that way perpendicular to each meridian will be constant, and that corresponds to what? Well, remember the short quiz at the beginning of this episode, the set of points on the sphere that have the same latitude. That will be a parallel, a certain smaller or perhaps even an equatorial circle on the surface of the sphere. And the other thing that we may want to research is the following. Let's say the point that executes its motion like this with the requested property forming the same angle with each meridian gets closer, let's say, to the North Pole. What happens then? Well, in this case, its latitude will tend to, let's say, positive pi over 2. That's when it goes to the North Pole. When the point tends to the South Pole, then it will tend to negative pi over 2. But in this case, when the point tends to get closer and closer to, say, the North Pole, then what will we have over here? We will have the latitude phi getting to pi over 2, pi over 2 divided by 2, pi over 4, pi over 4 plus pi over 4, pi over 2. So the tangent of pi over 2 in the limit gets to what? To positive infinity. So this piece over here, the right-hand side, tends to positive infinity. And what does it mean? It means that if we fix the longitude lambda, it will be intersected by our trajectory. How many? Infinitely many times. It means that our curve will behave somewhat nicely between the poles, but when this point will get closer and closer to each pole, let's say the North Pole or the South Pole, it will start spiraling or winding around the corresponding pole and getting arbitrarily close to it, but not reaching it. So our curve will go like this, in some nice way across the entire sphere, and then it will, as it gets closer to the North Pole, let's say, it will wind into a tighter and tighter spiral, and the same thing will happen on the other side. And for my previous research, for the case when the angle beta is 0, actually, that's perhaps this expression over here, this form of that describes the shape of the Loxodrome is more advantageous, because when the angle beta is 0, then look at this. In the limit, again, we get positive infinity, let's say, over here in the limit. So in the limit of cotangent of beta, when beta tends to 0 staying positive like this, this will be positive infinity. And how do we manufacture positive infinity on that side? In the limit, when the longitude of destination tends to longitude of origin, which is to say that the longitude of the point in this case will be what? 1 and the same. It will be a constant. It will be some constant real number, and that precisely means when the angle is beta, our point moves around or along a given meridian. This is precisely the convenient way to look at it, and from this point onward you can investigate or analyze the equation of the so-called Loxodrome, as we promised at the beginning of this episode, on your own, investigate its features, and in some sense compare this situation with other curves where the trajectory of a moving point was crossing the corresponding minimizing geodesics or the generatrixes, as we saw in case of the right circular cylinder, under one and the same angle. Remember, in the previous problem that we solved, we came across a situation where a point wound its way over a right circular cylinder. These are the meridians, if you will, on the right circular cylinder, and the angle under which such trajectory intersects all these generatrices of a right circular cylinder was, again, the same, similar to how these things happen on a sphere. And we will solve one more similar problem where basically our point will be executing a motion over the outer surface of a rigid right circular cone. And over there we will see how these things will work out and whether the trajectory of that point will also intersect each and every generatrix of a right circular cone under the same angle. These are interesting things. You can start researching this on your own. Meanwhile, this will be it for the physics problem S3P7, and we will move on to a new challenge next. And our next challenge will be a problem in computer science numbered S3CS7, Season 3 Computer Science, problem number 7. And the objective of this problem is to construct a big O of n time and big O of 1 space complexity algorithm that can be used in order to detect whether an input integer can be represented as a sum of two integers taken from a sorted in an ascending order array. Let's say we designate this array in a traditional notation: a sub 0, a sub 1, a sub 2, a sub k, a sub n minus 1, for a total of n elements, because we begin numbering the elements in an array with the subscript number 0. So the last subscript is n minus 1. The total number of entries is n. And the fact that our array is sorted in an ascending order, this is just one order for definitiveness. It could be descending order, but for demonstration purposes, let us assume this array is sorted in an ascending order. That means that we have the following relation across all the elements in our array, which means that the deeper we wade into the array, then the more we have the following situation, that logically the next element is not smaller than the previous one. So that means that the element A0 is less than or equal to element A1, A1 is less than or equal to A2, and so on. AK is less than AK plus 1, and so on. AN minus 2 is less than or equal to AN minus 1 under these conditions, where to check if the given input integer x can be represented as a sum of two integers taken from this here array. Again, big O of n time big O of 1 space complexity. And we remember the caveat, of course, is that based or due to the fundamental theorem of arithmetic, every whole number, be that number positive or negative, can be represented in a unique way as a product of its prime factors, provided that we ignore the order of prime factors in that representation. So this representation is unique, but as a sum, evidently, every integer can be usually, especially if the integer is large enough, can be represented as a sum in a number of different ways. So here, of course, we want to make sure that our algorithm terminates on success on the first occurrence or on the first possibility to represent x, the input integer, as a sum of two elements. For example, there could be multiple elements in our array, which when sum will produce the integer x. We're not interested in an exhaustive search of all. We're just interested in the first occurrence. Somehow process this array according to the big O of n time and big O of 1 space complexity algorithm, and tell us if this integer x can be represented as a sum of two integers. The first occurrence of such a possibility to represent x as a sum of two integers is enough. At that point, the algorithm should terminate and return all the interesting information, for example, the locations of the indexes in the array or the actual integers that sum to the given input integer. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the computer science problem S3CS7.